Hi everyone, my name is Lydia and this is what I wish they taught me about econometrics and introduction. In this video, we're going to connect a few of the concepts that we saw in the past videos, and it's how distance turns into probability. We've talked about the z-scores, the t-scores, the tables for each of the z and the t distribution. We talked about the p-values, a very important key concept in econometrics. And here is the key question that we're going to answer in this video. How does a number like 2.1 suddenly become a probability, let's say like 0.036? Let's connect all of those dots together. Keep in mind, a z or a t-score is a distance, and we said that distance was in standard deviations as the unit. So whenever you're going to see the z distribution or the t distribution, you're always starting from the zero, the middle here, and you're moving one standard deviation in this direction, then another one, another jump here, so 2, and then we've got 3. And we do exactly the same on the other side, so we've got -1, -2, and then -3 here. And keep in mind, both the z and the t distribution are symmetric, so whatever probabilities we said we find on one side, on one half, we'll find on the other half as well. So a z-score, t-score goes in the horizontal axis. Okay? And that is telling you the distance. It tells you how far your estimate is from the null, measured in standard deviation units. So again, it's not a probability, it's a position on a distribution, where 0 is the center and large absolute values mean that you are very far away. But why distance alone is not enough? Why can't we just keep repeating all the time? So a z-score of 1.2 is a z-score of 2.1 and so on. A distance by itself doesn't tell you how surprising something is. A value of 2, which, for instance, we see right here, can be very extreme in one distribution, but not so much of an extreme in another distribution. So what matters is, well, how much probability lies beyond that distance? So where is that p-value in this case? Once you place your z or t-score on the distribution, so which we just did on the horizontal axis in here, you look at the tail beyond it. So if I picked 2 in here, it means for the p-value, I am looking at values beyond. So values bigger than 3, or that could be 3.5 in here, and so on. Now, this distance will determine an area, and the area is the probability, and that probability, then we called it the p-value under the null hypothesis. So as you can see, there is a 1-to-1 relationship between the absolute value of a test statistic and the p-value. So 1-to-1 relation, meaning to each t or z-score, okay, you can assign a p-value, because you can always look beyond that z or t value. Now, what is this 1-to-1 relationship? Because you might have heard that there is an inverse relationship between them. And these graphs makes it very clear. When you start going in this direction and you're increasing your z or t-score, what you're doing is you're making this area all the time smaller and smaller. Okay, so in absolute terms, the bigger the z or the t value, it means the smaller the p-value that it's associated with it. And the opposite, smaller z or t's will mean larger p-value, okay? This graph obviously makes it clear. Now, when you use one tail or two tails, because we saw that for the t-table, obviously that depends on your question. And we said that on a one-sided test, you have the area all in one tail. On a two-sided one, you have area in both tails. That's why the same test statistic, keep in mind, can give different p-values depending on the hypothesis. So same test statistic give different p-value depending on null. And I'll write here as a reminder, one-tailed or two-tailed. In the previous video, we saw like how those different numbers came about as well. So again, a reminder, now that we know that there is a one-to-one relation between z-t-score and the p-value. Now, tables and software do the same thing. So if you're doing it through Stata, through R and the like, you're just replicating the numbers that you see in any tables that is printed out there. Tables, keep in mind, convert the distance and it gives you the area manually. The software can do that conversion instantly for you. So just different tools, same logic behind it, but now you also know what is the logic that that software is using. There is, however, a common misunderstanding that comes out of this relation between the z and the smaller p-value, and the misunderstanding is that a small p-value means a large effect or means an important result. And this shouldn't. Now that you know the meaning behind the p-value, this shouldn't be a misunderstanding that you have anymore. So a small p-value does not mean that you have a large effect, does not mean that you have an important result. It only means the distance would be hard to explain if the null were true. Okay, so magnitude and significance are different ideas. So overall, in this video, what we saw is that test statistics measure distance, p-values measure probability, one turns into another through the shape of the distribution, and now we know that there is a one-to-one relation between z or t-score and the p-value. So hopefully with this video, now you should have a full picture of like distributions, tails, tables, p-values. In the next video, I'm going to show you a little bit more the relation between one-tailed and two-tailed values and what are some of the most common values in terms of like z/t score that students should be remembering. And whether you like it or not, you'll be hearing them so much that you will end up memorizing them anyway. But it would be important for you to understand where these numbers come from and why they make sense to memorize. I'll see you in the next video.